It works. So this doesn't matter if I go to the screen and show some things, or do you want to record it?
My friend, my colleague and friend, would record everything. You can do it?
Yeah.
A laptop? Ah, that's very good. The price is the division. I get pleasure to recite István Gaál from the previous university to give us this lecture, and I am very grateful to you and all the participants. I get to you to come to give us these lectures in our country and to meet you in our university.
Thank you very much. So it is a very great pleasure for me to be here, and I'm very thankful that Professor Hussein Zafari for his very, very kind invitation, which made possible that I could come here and could bring also my wife along. And, after many years that I was leading researchers of this university, and after many years that I also met researchers of this university online. Now it is a great pleasure to be here personally and to meet you face to face. So, according to our discussion, there will be two parts of this lecture. As you know, our joint research topic with Professor Fadil is the monogeneity and power integral basis of algebraic number fields. That will be more or less the second part of this lecture tomorrow. And today, as an introduction, I would like to give you an overview about several methods for solving Diophantine equations, because what I was doing during my research career is that I was trying to solve certain Diophantine equations, which where the solutions produced numerical data according to generators of power integral basis of algebraic number fields. So, well, a Diophantine equation in general is a polynomial equation with rational integer coefficients and several variables where the variables are also integer numbers. So the main problems according to Diophantine equations is to find out whether or not there exists a solution, whether or not the number of solutions is finite or maybe infinite, and the most interesting problem is to find the solutions. Well, I like to insert some photos. Some people say that this was Diophantus. Nobody is sure about it, but actually he wrote a series of books about arithmetics. Only some of them were found, but actually these are the ancient roots of the researches about Diophantine equations. Anyway, in the year 1900, at the famous conference, David Hilbert posed 10 problems, and the last one of them was to ask whether or not it is possible to find a general algorithm for solving Diophantine equations. This problem was answered by Yuri Matyashevich 70 years later. This was a result in mathematical logic, and the result was negative, that such a general algorithm does not exist. In mathematical logic, this theorem is formulated in the following way: every computable enumerable set is Diophantine. Well, this is on one hand an unfortunate result that there is no general algorithm. On the other hand, we are lucky because we have a long series of research topics, because we have the chance to develop methods to solve several types of Diophantine equations. Matysiewicz is still alive. Here, that has died in 1943.
In which country?
Sorry?
In which country?
He was a Russian. He was a Russian mathematician.
And now he is alive.
He's alive, yes. There are several types of Diophantine equations. The starting point of all new methods for solving Diophantine equations was the so-called 2E equation. I shall describe it within a short time, and there are several generalizations of this type of equations, just like norm-form equations, index form equations, resultant type equations, and so on. The results concerning these equations are of several types. First, some results, the first results show that there are only finitely many solutions. Then there were estimates for the number of solutions, and then there were calculated some upper bounds for the sizes of solutions, and these upper bounds were huge. You will see it later on. So there were methods to reduce these bounds, and these reduced bounds are still relatively large, so we also needed to develop some algorithm to test all possible solutions under the reduced bounds. It will be more clear as I go through these methods for 2E equations. So what is a 2E equation? This is a polynomial equation, f of x and y equals m, where f is a homogeneous polynomial with rational integer coefficients of degree at least 3. So the first and second degree equations are not interesting. The first degree equation is a linear equation, the second degree equation is a Pallian equation, which are well known. But starting from degree 3, they have some common properties. Without restricting the generality, it is allowed to assume that the leading coefficient of this polynomial f is equal to 1, and then calculating the roots of the polynomial fx1 equals 0, we can factorize the left-hand side. Of course, this alpha 1 and so on, alpha n, they are the conjugates of certain algebraic number alpha of degree n. Now, we denote by beta j. Well, the starting point is that we assume that x and y is an arbitrary but fixed solution of the equation, and then we derive estimates for the sizes of x and y. So for this fixed solution x and y, we denote by beta j the jth factor of the left-hand side of the equation, x minus alpha j times y. And so among these factors there are large ones and there are small ones. I is going to be the index of the smallest one. This smallest one is certainly less than the nth root of the right-hand side, so it is certainly less than or equal to the nth root of the absolute value of m. And it is easy to show that, on the other hand, all other beta j of the left-hand side of the equation cannot be very small if the variable y is large enough, because you have here the triangle inequality. Beta j minus beta I is just alpha j minus alpha I times y, and beta I is less than or equal to the nth root of m, and this expression is larger than, let's say, alpha j minus alpha I over 2 times the absolute value of y. If y is not very small, we can assume that y is not very small, because the small values of y can be just substituted into the equation, and then we have a polynomial equation in one variable x, and we can easily decide whether or not that equation has an integer coefficient. At the very beginning of my talk, I wanted to ask you to stop me if I am speaking about things that are very well known for you, and tell me if I'm going too fast or too slow, so everything is up to you. So there is a small factor, beta I, and all other factors are relatively large, larger than constant times y, if y is not very small. But then we can write the equation in this form, so beta 1 and so on, beta n are the n factors of the left-hand side, and then we give an estimate for the smallest factor of the equation. So beta I is, of course, equal to m over the product of the remaining factors, and all these remaining factors are larger than constant times the absolute value of y, which implies that the smallest factor of the equation is indeed very small. It's less than constant over the absolute value of y to the power n minus 1. If we divide by y, then we arrive to an inequality saying that x over y, this rational number, must be a very good approximation of the algebraic number alpha I. Here I have also calculated this constant C1, which are, well, actually we can calculate the exact values of these constants, but they are not so very important. The important is that this inequality holds. Of course, until now it was completely elementary, and then came the Norwegian nobleman Axel Thue, who liked mathematics, and he has proved the following inequality. Which is a strengthening of the well-known approximation theorem of Lagrange or Lejeune, saying that any algebraic number of degree n cannot be approximated better than in order n. So the improvement of that theorem, the theorem of Thue, says that this algebraic number alpha of degree n cannot be approximated better than in order n over 2 plus 1 plus epsilon, where epsilon is a small positive constant. More exactly, his statement says that for any small positive epsilon, there exists a positive constant c, such that this inequality holds. Applying this inequality and comparing it with the classical approximation theorem that any algebraic number of degree n cannot be approximated in order better than n, we obtain that, so comparing the lower estimate and the upper estimate, we obtain that y has to be smaller than the disadvantage of, well, the advantage of this theorem, let's start with the advantage, is that it says that y has to be smaller than a finite constant. It implies that there can only be finitely many solutions. On the other hand, in this theorem of 2e, we cannot explicitly calculate this constant c. The method does not give any idea how large this c can be. Therefore, we have no idea how large this constant c, the upper bound for y, can be. So the theorem of 2e is a kind of ineffective statement saying that there are only finitely many solutions, but not giving any explicit and explicitly calculable upper bound for the sizes of solutions. There will be also so-called effective estimates for the sizes of the solutions, which originate from Alan Baker in the end of the 60s. I shall speak about it later on, but as a next step, let me mention an algorithm which was developed by Attila Pető for calculating the so-called small solutions of 2e equations, or even 2e inequalities. Actually, if you test some of these equations, then it will be very clear from the very beginning that these equations only have very few and small solutions. This algorithm makes it possible to calculate all solutions of the 2e equation or 2e inequality up to a very large upper bound. Yes, for this method it is necessary to assume that, so this method calculates only the co-prime solutions. If the solutions are not co-prime, then the common divisor of x and y divides the nth power of the common divisor divides m, and then you can divide with this common divisor, so the solution of any type of 2e equation can be reduced to solving a 2e equation where we are only interested in the co-prime solutions. So this method is a very simple one, using only the continued fraction algorithm and making possible to calculate all solutions where all co-prime solutions where the absolute value of y is less than a large number, let's say 10 to the 500. So if we calculate all solutions up to 10 to the 500, then we can be pretty sure that we have obtained all solutions, because, well, no one of us has ever seen a 2e equation with a solution larger than 10 to the 500. So on one hand, this method makes it possible to calculate the solutions, which are all solutions with a very high probability. On the other hand, this method does not prove in a strict sense that there are no other solutions. But you will see that to prove that there are no other solutions, it yields the application of difficult methods, and it needs further calculations. So the method of Attila Pető relies upon the inequality that we have seen formerly, that if y is not very small and the factor number I as the smallest one on the left hand side of the 2 equation, then x over y is a very good approximation of this algebraic number alpha I. So x over y is an approximation of alpha I of order n. We have assumed at the beginning that n is at least 3, so again, if y is not very small, then this right hand side is less than 1 over 2 times y squared. Now it is well known from the theory of Pellian equations that Lejeune theorem implies that if this inequality holds for this real number alpha I, then x over y has to be a convergent in the continued fraction expansion of the real number alpha I. On the other hand, it is a little bit less known, but also very elementary, that there is also a lower estimate for the difference of the approximated number alpha I and the convergent, telling that if we denote by A sub k the partial quotients in the continued fraction algorithm, then this difference is larger than 1 over A k plus 1 plus 2 times qk squared, where again A denotes the partial quotients and P over Q are the convergence in the continued fraction algorithm. So we start from this inequality and we calculate the partial quotients of the algebraic number alpha I in the continued fraction expansion of alpha I until the denominator of the convergent exceeds our bound C, which is about 10 to the 500. You know that, well, certainly many of you have already calculated the continued fraction expansion of certain numbers, that the denominators of the convergence grow very fast. So to reach this bound 10 to the 500, it's about 400 or 500 steps, and it is an easy calculation. But if A is the maximum of the possible partial quotients, then this quotient is certainly larger or equal than 1 over capital A plus 2 times qk squared, where qk is still the denominator of the partial quotient of alpha I, which is actually x over y. So if here the Lejeune theorem implies that x over y is a partial quotient of alpha I, and if this partial quotient is pk over qk, then obviously x is equal to pk and y is equal to qk, up to sign, let's say. So then we have such an inequality on the lower bound, and we still have this upper bound. And if you compare the lower and upper bounds, then you obtain an upper bound for y. So if y is any solution of the original 2 equation, such that the absolute value of y is less than 10 to the 500, then y also satisfies this inequality. On one hand, y is the denominator of a partial quotient in the continued fraction algorithm of alpha I. On the other hand, y satisfies this inequality. Also, if you already calculated continuous fraction algorithms, then you know that these partial quotients are very much stable. So the partial quotients are usually very small numbers with 1 digit. Sometimes they have 2 digits or 3 digits, but one has to search for certain numbers having a continuous fraction algorithm with a partial quotient having 4 or 5 digits. So even if we go very far in the continuous fraction algorithm of alpha I, these partial quotients stay to be relatively small. And then, having this inequality, we finally only have to test all those, the numerators as in the role of x and the denominators in the role of y of the convergence in the continuous fraction algorithm of alpha I. We substitute them into the original equation, and then we can decide whether or not they are solutions. Let me give an example if you are interested in it. So it's very easy to explain an algorithm in general, but I always only understood the algorithm after having tried it by myself. So this is a very simple third degree 2 equation. Well, in this case the x and y can only be co-prime, and our purpose is to determine all solutions x and y with absolute value of y less than 10 to the 500. Now we calculate the roots of fx1 of the left-hand side. We have one real root and 2 complex roots which are conjugated to each other. And then there are 3 cases. We have to consider all of these 3 cases according to which factor on the left-hand side is the smallest one. Now denote by J naught the smallest one, and then the factor number J naught must be less than or equal to 1, and then the remaining factors are larger than constant times y. According to these numerical data, they are larger than 1.11 times the absolute value of y, if y is at least 8. At the end of our calculation, we can substitute all integers between -8 and +8 into the original equation, and to test whether or not there is an integer solution x corresponding to y. Then we have this approximation theorem telling that the smallest factor is less than or equal to constant over y squared. Now there are 2 cases. It is much easier to deal with the factor if alpha j is a complex number, because to complex roots there can only correspond small solutions of the equation, because if alpha j is this complex number, so we have these complex roots of the equation, and this is less than constant over y squared, then calculating the imaginary part of the left hand side, we obtain that y null 0.56 times the absolute value of y is less than this fraction, which says that y cubed is less than 1.44. So y can only be 0 or 1. So this is the less interesting case. the interesting case is always when the root is real. And in this case, as a consequence of this upper bound and as a consequence of Legendre theorem, we obtain that x over y is a convergent in the continued fraction expansion of alpha 1. Now we start to calculate the continued fraction expansion of this root alpha 1, and we find that in the step number 957 we exceed the bound 10 to the 500 with the value of the denominator of the convergent, and then we calculate the maximum of the partial quotients of the corresponding convergent. Well, here you can see how the denominators of the partial quotients grow. So in almost every step, the partial quotient is 1 digit longer. So we reach the bound 10 to the 500 in about 900 steps. On the other hand, these are the denominators of the convergence. On the other hand, the partial quotients stay to be very small. So even if we go very far in the continued fraction algorithm, they remain stably small. So 1, 2, 5, 7, 10, sometimes 100 or 600. And it is very surprising that if you go until 10 to the 500 with the denominator of the convergent, then you see a very nice and very exceptional partial quotient being equal to 22,054. So that is an exceptional case, but still with that value, using the lower and upper estimate for the difference of alpha 1 and the convergent, we obtain that y is less than 17,900. So all what we have to do is, first of all, to substitute the numerators and denominators of the convergence in the role of x and y into the original equation. These are all of them, to see whether or not they are solutions or not. And we also have to deal with the small values, because at the beginning of the estimates we have assumed that y is large enough, and we have assumed that y is larger than 8. So we also substitute these small values of y, and then we finally obtain that this equation, as usually, only has a small number of solutions, and also these solutions are indeed very small. So if we calculated all solutions up to y less than or equal to 10 to the 500, then well, it's almost sure that we have obtained all solutions. On the other hand, to prove that there exist indeed no further solutions, we have to apply the method developed by Alan Baker and some consequence of it. How much time do I have? 12 or? Half past 11. So shall we break now?
Not yet. 30 past 11.
Yeah, so in 20 minutes.
In 42 minutes, exactly.
Okay.
We'll take a break, small break.
Yes. Okay. So let us turn now to the so-called effective methods. Effective methods for Diophantine equations always mean that you give some explicitly calculable upper bounds for the solutions. So we remain at the study of two equations because all these methods were originally developed for two equations, and it is a very good example of Diophantine equations to visualize, to present these methods. Later on, of course, there were several generalizations of these methods, and they were applied to norm form equations, to index form equations, and to some other types of equations. So we denote by, so n was the degree of the polynomial f, and alpha was a root of it, and we are going to denote by k the number field generated by alpha over the rational field, and we need the unit rank r of this number field k, and the regulator of this number field, and k is going to be this number, and capital H is going to denote the height of the polynomial, which is the maximum absolute value of its coefficients. Now, in 1966 and 67, Alan Baker gave effective lower bounds for certain linear forms in the logarithms of algebraic numbers. I shall show you these inequalities in a few minutes. And as a consequence, 1 or 2 years later, he developed an effective upper bound for the solutions of the two equations. Later on, there were several improvements of these lower bounds concerning linear forms in the logarithms of algebraic numbers, and using these improved lower bounds, there were some improved upper bounds for the solutions of the two equations developed, for example, by Jan Bujold and Karma and Győri. But still, if you see, these are huge bounds, so they imply that there are only finitely many solutions. They imply that in mathematical principle, in a theoretical sense, there exists a finite algorithm to determine all solutions, because under this tiny bound there exist only finitely many possible values of x and y, which can be tested in a finite amount of time, and then this is in theory, it is an algorithm to determine all solutions. The problem is that if n is equal to 3 and k is 100 times 3 times 4, and then n is, you take n to the power k squared and you take the exponential function, then you obtain such a huge number, which is larger than the number of atoms in the universe. So in practice, these theorems give no chance to determine all solutions. So if someone states that, well, I have constructed an algorithm to determine all solutions because I gave an upper bound for the solutions, don't believe, because these upper bound purely applying Baker's method, in principle they give an algorithm, but in practice there is no chance to determine the solutions, only based on these theorems. But let me try to show you how these upper bounds are derived. So this beta was the factor x minus alpha y of the two equation, and on the right hand side of the two equation we had the number m, which means that this algebraic number beta is of norm m in the number field K generated by the algebraic number alpha, and these eta 1 up to eta r are the fundamental units of the number field K. So any algebraic integer beta of norm m can be written in this form, where mu is one of the finitely many non-associated algebraic integers mu in the field K with norm m, and this is a power product of the fundamental units. So in the following, instead of the variables x and y of the original equation, we have now the variables a1 up to ar, the exponents of these fundamental units. Now we take conjugates of this equation, and we take absolute values and logarithms, and we divide by mu. Then we obtain such a linear equation for each conjugate j of the equation. Now, excluding the smallest conjugate beta I, for all the other conjugates we have such an equation. You know that there are the number of the unit rank of the number field is s plus t minus 1, and the number of real and imaginary conjugates, taking only one conjugate from the pairs of the complex conjugates, that is s plus t. So if we omit the conjugate corresponding to the least value of the left hand side, then we obtain a system of linear equations in the variables a1 and so on ar, consisting of r equations and r unknowns, and the determinant of the fundamental matrix of this system of linear equations is just the regulator of the number field. So you can actually solve this system of linear equations in the variables a1 and so on ar by using Cramer's rule, and then you obtain an upper bound for capital A, the maximum of these, the absolute values of these exponents, and using the fact that betas are less than constant times y, you finally obtain that the maximum of the absolute values of these exponents is less than or equal to constant times the logarithm of y. So this is only a technical inequality. And then the heart of this application of Baker's theory is actually the so-called Ziegel's identity. Ziegel was also a mathematician studying two equations at about 1930. The relative analog of two equations when the variables of the equation are algebraic integers of a number field instead of rational integers. So that's why Ziegel is famous, and at that time he was already applying this equation. So beta was x minus alpha times y, and if you substitute here the conjugates beta I, beta j, beta k, where I, j and k must be distinct indices, and still I corresponds to the smallest factor of the left hand side of the equation, then x and y falls out, and then you obtain 0 on the left hand side. So this is the well-known Seeger's identity. Then from the identity, if you divide by, if you put this term on the other side and you divide by it, then you obtain this equation, which holds for any three conjugates of the equation. Now, in the following, we are going to use this identity, that saying that for any complex number x, if x minus 1 is in absolute value small, then the absolute value of the logarithm of x is less than 2 times x minus 1. We shall apply it here. So if that is going to be x, and if if x minus 1 is small, so we shall see that this is small, then the logarithm of x is less than 2 times x minus y. But how to come to these inequalities? So this what you see here, this capital lambda is the logarithm of this side of the equation. So beta was mu times eta 1 to the a1 times eta r to the a r. So if you substitute instead of beta this mu times the power product of the fundamental units, then the logarithm of this side the logarithm of this fraction, the logarithm of this fraction, yes, of course, the logarithm of this fraction will be equal to lambda, and the logarithm of this side is less than or equal to 2 times the fraction minus 1. And of course, if you omit absolute values, then you still enlarge the difference, and then this fraction minus 1 is equal to the other fraction, so you obtain here the other fraction, and here you use that beta I is the smallest factor of the equation, and as you have seen it formerly, beta I is very small. Beta I is less than constant over the absolute value of y to the power n minus 1. On the other hand, any other factor, beta j, is larger than constant times y. Altogether, this fraction is less than or equal to constant times y to the power minus n. Now we obtain that this linear form in the logarithms of certain algebraic numbers is less than constant times y to the power minus n. And here you have to use this inequality. The logarithm of y is larger or equal to a over a constant, implying that minus the logarithm of y is larger than constant times a, which yields that this linear form in the logarithm of algebraic numbers is less than or equal to constant times an exponential function of constant times minus a. These constants can of course be explicitly calculated, but you will see that these are relatively small constants compared to some other constants appearing in the linear form estimates of Alan Baker. So the application of this method of Alan Baker yields that this linear form in the logarithmos algebraic numbers, we have shown on the former slide that it is less than an exponential function of minus a, and on the other hand, Baker's method implies that such a linear form is larger than e to the constant times the logarithm of a. And this is the very deep inequality which gives the essence of Baker's method. Now if you compare the lower and upper estimates in this inequality, you obtain an upper bound for the maximum absolute values of the exponents of the fundamental units. This upper bound for a simple cubic 2 equation with small coefficients is about 10 to the 30, and this large number is due to the fact that this capital C is a very large number. I shall show you on the next slides the original estimates of Alan Baker. Now if the maximum absolute value of the exponents is less than, let's say, 10 to the 30, then the absolute values of the factors are about less than about the exponential function of this value, and so this is the way as you obtain such very large, very large upper bounds for the solutions of the 2 equation. Alan Baker has passed away some years ago. He obtained a Fields Medal in the beginning of 70s for his very famous method giving lower bounds for the linear forms of certain algebraic numbers. So how such an estimate works? So they introduce certain heights of algebraic numbers. If alpha is an algebraic number of degree alpha and a naught is the leading coefficients of its minimal polynomial, then this number is quite well known as the absolute logarithmic height of the algebraic number alpha. And then if you have several algebraic numbers and you take the principal values of their logarithms and the number field k generated by these numbers over the rational field q, and this field is of degree d, then they introduce this other type of height denoted by h sub I, which is the maximum of the absolute logarithmic height 1 over the degree and this number, and then they create this linear form in the logarithms of algebraic numbers with rational integer coefficients in this case, but there are some generalizations telling some generalizations also for the case when the coefficients are algebraic numbers. And shortly formulated, one of the typical estimate of Baker type theory given by Alan Baker and Gerhard Wistholz in 1993 says that the logarithm of the absolute value of this linear form is larger than this number, and here this capital C, you can see that it is a huge number, and this huge number implies that also in our estimates for the absolute values of the solutions of 2 equations will be very large. Actually, these estimates of Alan Baker are very general, and many mathematicians say that they are in fact weak estimates containing such huge constants, and the weakness of the estimates is because they are very general. On the other hand, they are very general. So I think I shall stop here, and then shall we continue?
Yeah.
What time? And how much time shall we have in the second part?
An hour. An hour plus
An hour. Okay, yeah. So then thank you very much. Shall we take 5 or 10 minutes break?
Yeah.